Hey Royals, in this lesson we're going to look at how to graph uniform motion. Now uniform means that the motion doesn't change. So a nice way of looking at that would be that the velocity or the speed of the object is not changing. So I'm going to say speed, velocity remains constant. Okay, so that means that we don't have any acceleration occurring in our problems today. But we're going to go ahead and try to calculate some accelerations and whatnot. All right, so graphing uniform motion. If I look at this first graph here, it's for 4 people that live on the same street and they are going to meet for some coffee. And the first thing we want to do is we want to identify what is actually happening in this graph. Okay, so that's going to be a skill that we're going to develop throughout this lesson, is to be able to define or describe what is occurring inside a position versus time graph, or a velocity versus time graph, or even further, an acceleration versus time graph. Okay, so if we look at person 1 and try to explain what is occurring with their motion, well, I'm going to notice that person 1 starts their motion at 50 meters east. So I'm going to say starts at 50 meters east. Oops, that's W. That means west. So east from home. And travels. So which way are they traveling? Well, they're starting away from home. So they're starting at 50, but they're heading towards 0 for position. And that's from home. So if I'm getting closer and closer to home, that means I'm traveling west, because I'm actually traveling in a direction that causes my position to decrease. And because my position is measured away from the object, if I'm getting closer to the object, I'm moving towards it. So, and travels west. Okay? So object, or person 2 in this case, person 2 is represented by the circles. So that's person 2 here. So I'm going to do it in pink, and person 1 will remain in black, I guess. Person 2 starts at home, because their distance away from home, or their position relative to home, is 0 at the beginning. And they are moving and travels. In this case, they're moving away from home because their position is getting larger. So we're going to say, and travels east. All right. So now let's move on to person number 3. And I'll do that person in green here. So green will represent person 3. So I'm just going to go all the way along the line. All right. So person 3 is represented in green. So they start right here. They start at 10 meters east of home. So start at 10 meters east from home and travel. And again, their values are getting larger, just like person 2's was, which means that they're traveling east as well. Okay? And then person 4, we will represent them with the blue, and they are represented in stars, and I try my best to draw the stars. Here we go. And you can see that their position initially was 30 meters east of home. So I'm going to say starts at 30 meters east from home. And what are we going to say? Well, their distance doesn't change, or their position doesn't change, which means that they're going to remain at rest. And remain at rest, meaning they're not moving on us. Okay? So the steepness of this line, if we think about the steepness of the line, and we're going to say the slope of a position time graph, if you look at these, it's all constant. The steepness of those lines doesn't change. So person 1 has a line and it's not changing or curving at all. So that means that it remains constant. And this is what we refer to as uniform motion. The motion doesn't speed up or slow down. Okay? So in fact, the slope of this actually represents the velocity. So we can find out how fast these people are moving just by calculating the slope of their lines. Okay? So what I need to do is, and I'll do the first one, and then I'll just give you the answers for the other 3 people. But one thing we want to remember is that when we're looking at our graph, we want to pick values that are right on what I call a crosshair. So this one here is at 1 and 45. So it's 1 on the x-axis. So if I trace it all the way up, it reaches the line and it's at 45. I'm also going to use this value right here, which is at 9 and 5. Right? I do not want to use, say, this value. That value is a poor choice because you're guessing on the y value. Yes, you may understand what the x value is, 2.5, but that y value you're going to have to guess at. So we're going to try to stick away from that. So we'll put a little note on the side here. We're going to say, recall when we calculate the slope, comma, use points that intersect axis grid lines. Okay, and that's just a memory tool for us so that we don't make any mistakes when we're actually calculating slopes. Okay, and I'm also going to use points on the actual line of best fit, not my data points if I can. But in this case, my 2 points that are on my line of best fit are in fact data points as well, which makes life easy. Okay, so we're going to go ahead and say that the velocity is, it should be in black because that's person 1. We represent it as the black ink. So the velocity is the change in position divided by the change in time. And you'll look at this and go, wait a second, that's not the slope equation. It is actually, because my position is my y-axis. So change in my y values would be change in position, d2 and d1. And my change in time, which would be my x-axis, would be my denominator in my slope equation. Okay, so let's go ahead and substitute in the values. I get, like, my first one was 45 meters, and we'll say that's east. Subtract the final position. Sorry, I have actually made a mistake here. The first one I should be using is my final position of 5 meters. Subtract the 45 meters east. So 45 meters east. And I'm going to divide that by 9 seconds, subtract 1 second, which gives me 40 meters a second east, and it's negative divided by 8 seconds, which gives me negative 5 meters a second east. Well, negative meters per second east is actually in fact the west direction. So if I'm thinking about the negative east direction, that's the west direction. So I can actually call this the positive 5 meters a second west instead of using a negative east. Okay. Now, if you looked at this, the same situation would happen with the slope calculations for the other 3 people and their values, and I'll just write them down. I'll write them in red here. Value for person 2 is going to be 2 meters a second east, and you should try calculating these and checking it on your own. Person 3 will have a velocity, and we'll call them 2, and we'll call a little 1 there. Velocity for person 3 is 4 meters a second, and it will be east. And then person 4 will be a velocity of 0 meters a second. And I don't need to put a direction on it because it's 0. It doesn't have a direction. Okay, so now I know the velocities of each of these people. We can go ahead and actually graph their velocities. And just reminding ourselves, we're using black ink to represent person 1. We were using pink to represent person 2. So I'm going to use pink to represent person 2. I believe green was person 3. And then I believe blue stars were person number 4. Okay, so if we try to graph this, person 1 was moving at 5 meters a second west or negative 5 meters a second east. That means that their line is right here. This is person 1. And that means that they would have a velocity that remains constant at negative 5 meters a second east, or 5 meters a second west. Okay, so if we look at person 2 had a value of 2 meters a second east. So theirs is going to be straight across at the 2 meters per second east mark, and they can have dots. And because it's not changing, I'm just simply putting dots down at random locations across my line. Okay, person 3 had a value of 4 meters a second east, and so their velocity graph looks like this. And we can put down triangles to represent this person and their velocities. Okay, so there's person 3, and then we can demonstrate person 4. Their velocity was 0, so they're just straight across the x-axis pretty much. So they have little stars, and I'll just do my best to draw little stars here. And again, they're just randomly placed because it's not changing, right? I could calculate it at each of these positions on my graph, and they would still give me the same velocities for each of the people. Okay, so we now have the ability to determine the acceleration of each of these people. Now, acceleration, if we remember, acceleration is a change in velocity with respect to time. So if I'm looking at that, it would just simply be this equation here. Well, the change here is not going to be anything because our slopes of each of these lines is 0. And we can demonstrate that. We can say that I'll take person 1 and I'll say that their final velocity at this point right here, it was negative 5 meters a second east. And their initial velocity, which was, let's say at this point, is negative 5 meters per second east. So we should see that their accelerations don't change. So 5 meters a second east, and it's negative. Subtract negative 5 meters per second east. And if I divide that by any times, let's say 10 seconds minus 1 second, really doesn't matter what the denominator is, what 2 points you chose on that horizontal line, because the numerator is going to give you 0 meters per second, and you're going to divide that, I guess, by 9 seconds, and you're still going to get a acceleration of 0 meters per second squared. Okay, so all four people have an acceleration of 0 meters per second squared. Okay, now, so what have we just discussed here? Well, we have just basically said that if I had position and I wanted to get to velocity, it's a position versus time graph, and I wanted to get to a velocity versus time graph, what could I do? Well, I could calculate the slope of the line. And that's what we did in our first step here. We said, I want to go from this position versus time graph and change it into a velocity time graph. And we calculated the slope. And then once we are at a velocity time graph, we wanted to get to an acceleration time graph. Acceleration versus time. And what did we do again? We calculated the slope. That's what we did just above here, where we calculated the slope of a velocity versus time graph, and we got the acceleration. Okay. Now, it is possible to go back the other way. If I gave you an acceleration time graph, you could get a velocity time graph. Or if I gave you a velocity time graph, you could get a position time graph. And this is done by calculating the area under the curve. Okay, so we're going to do an example of this together. And then there's a few that we'll do together in class as well. Okay, so if I look at the very first one here, this, I see two rectangular shapes and then kind of a flat region in between them. So we know how to calculate the area under the curve. And when we say under the curve, we mean between the line, right, and the x-axis. So I'm calculating the area here, and between the line and the x-axis would give me this rectangle here, right? And then we also have this section in the middle. Okay, we know that the area of this line here would be 0 meters a second, right? The area of that line is 0 meters per second. And we're starting with an acceleration versus time graph. Okay, so we know that if I'm going to try to go backwards on my order of operations, I'm going to find the area, okay, under the curve. I'll just fix that curve. Okay, so let's find the area of the red section here. So the area we know is going to be length times width. So the length of this rectangle is 3 seconds. And I multiply that by the width, which is 2 meters a second north, which gives me, meters per second squared north. So if I multiply this together, I get 6 seconds times meters divided by seconds squared. So that gives me meters per second north. So I now know that for this section here, my velocity in that first section is going to be 6 meters per second north by the end of it. Okay, so by the end of this section here, at 3 seconds, my velocity will be 6 meters a second. So that means at 3 seconds, I'm going to have a velocity of 3 meters a second. Now, initially, it was 0. We're assuming that, and we're going to draw this line in here. That's going to be the red section that we have just identified. Okay, the pink section, you know that the length times width of that is nothing. So that means that my velocity is going to be unchanging. So it's going to remain at 6 meters a second. So that means that my velocity doesn't change over the course of that next 2 seconds. So at 5 seconds, it's still 6 meters a second. This is telling me how much my velocity is changing by. Because the acceleration 0 means that my velocity doesn't change. I bet there's some people that thought I should draw a line down at the very bottom here. And that would indicate that my velocity went to 0. No, we have to remember that acceleration represents change in velocity. So the fact that my acceleration is 0, my velocity remains constant. Okay, now the last section here, this rectangle here, has an area of length times width. So my length in that section there would be 4 seconds, and my width would be -2 meters a second squared. And I'm using negative because it actually came out to be a negative value. And that gives me -8 meters a second, and that's in the north direction, which is 8 meters a second south. So that means I have to decrease my velocity by 8. Now it started at 6. So that means over the course of the next few seconds, 4 seconds here, it needs to decrease by 8. So it's at 6 minus 8 gives me -2. So at 9 seconds, it has to be at -2 meters a second. So I can draw this line in here, and that would represent the blue section. So now I've changed my acceleration versus time graph into a velocity time graph. And let's go one step further and make it a position versus time graph. Okay, so the position time graph, in this case, I again want to calculate the areas under the curve. Okay, so I'm going to say I see a triangle underneath this curve, and then I see a rectangle in the middle here. So I'll calculate the area of that rectangle. But then we have to remember this, the area under the curve. So that means between the curve and the x-axis, there's a triangle here, which only goes down to 8 seconds. But then there's another section that shows up here for that last 1 second. So we need to actually calculate 4 areas for this velocity versus time graph. So we'll jump in here. So this first one is a triangle, so 1/2 the base times the height. So 1/2, the base length is 3 seconds. So 3 seconds multiplied by the height here is 6 meters a second. And if I multiply that together, I get 1/2 of 3 multiplied by 6, which gives me 9 seconds multiplied by meters per second, which is 9 meters. So I need to increase by 9 meters. That's 9 meters north. So I'm going to assume I start at 0. So over the course of 3 seconds, I need to increase to 9. Now, it's not going to be linear, meaning straight, because I am accelerating during that portion of time. So what that means is I could actually calculate how far I traveled in 1 second, and then I could calculate what I traveled in 2 seconds, and then I could do it 3 seconds. So at 1 second, the area of just this section here, if I wanted to just look at 1 second, it would be 1 times 2. We'll do that one kind of in green, I guess. Oh no, I don't want to do green because it's another color I picked. We'll do that one in red. So area would be length times width. My length would be 1 second, divided by 2, divided by 2, multiplied by the height of 2 meters a second, which would give me 1/2 of 1 times 2 is 1 meter a second. Right? So, or sorry, 1 meter. 1 meter. And that's in the north direction. So in the first second, I've only actually gone 1 meter. And then at 2, it would be a matter of 2 times, at 2 it's 4. So I would be going 4 meters. And it doesn't really look quite like a straight line anymore. It, in fact, is curving upwards. So our line actually, if I can draw it properly, is curving upwards because the curve means that we are experiencing acceleration. Now, between the pink section here, let's look at the pink section. Pink section is 2 meters long. It's a rectangle. So I can say area is equal to length times width. My length is 2 seconds. My width is 6 meters a second north, which gives me 12 meters north. And it does not have a change in velocity. My velocity remains the constant, which means that my position is going to change linearly. So that means it's going to increase by 12. So I'm at 9 right now. I need to increase by 12. So that means that I'm going to go up to 21. So here is what I need to increase to. So 21 at 5 seconds. That's this location here. And it's going to increase linearly to that. So over this course of time, I increased by 12 meters. this period of time was 9 meters. And now we have to determine what's going on in the green section. So this green section is a triangle. So we'll say 1/2 the base times the height. So 1/2 the base in this case goes from 5 to 8, which is 3 seconds. My height is decreasing by 6. So that's -6 meters a second east. Or actually, sorry, it's still 6 meters a second east. North. I don't know why I said east. North. If I calculate this through, I get 9 meters north. So I'm still going to increase by 9 more meters. But notice that my velocity is decreasing, which means I'm slowing down, which means that my position is going to decrease by a curved line. So I'm at 21 and I need to increase by 9, gets me up to 30. So this will be 9 meters. So at 30, at 8 seconds, and it needs to curve downwards, be a concave down. Right? Now in the last section, blue, again, it's a triangle. So area is 1/2 the base times the height. 1/2 the base, which is 1 second. The height, which is 2 meters per second. And in this case, it's south, which means that I'm now going to decrease my position. I'm going to be starting to come back by 1 meter south. So that means that I need to curve down 1 meter in the next by 9 seconds. So it's going to curve downwards by 1 meter. And now that gives me my position versus time graph. Okay, so if you have any questions or anything, please reach out to me. We will be doing more of these types of graphing in class together.